renderforce.com.
Hello everyone, my name is Emad and today we'll be discussing M5, which is inverse Z-transform, which basically involves converting a function from the Z domain to the time domain. So it will be converting from a function in Z to a discrete time domain function in N. Actually, there is a formula for this. The formula is x of n is equal to this. But for this subject, we will not be using this formula. Instead, we will be using the pair tables. The pair tables are a set of tables in which there are pairs of functions that are interchangeable, such as there are two examples over here, which I will discuss in a while. So let me explain to you inverse Z transform using a few examples. The first and second example that I will do with two methods is h of z is 3 divided by 1 minus 3 by 4 z to the power of 1. So our question is to find h of n, which is the objective of this whole module. So we'll be considering two cases in which the row of region of convergence is in these two regions. Region number 1 is where z is greater than 3 over 4, which is outside this circle here, where the system is causal. The second is when z is lesser than 3 over 4, which is inside this circle here, which makes the system non-causal. Now, let's consider the first one. The first one is for this question using this formula over here, which can be found in the pair table, which is formula number 5. So, to find h of n, all we have to do is simply write this into this form. So we try to write it in this form. So we find h of z is equal to 3 outside a big bracket, 1 divided by 1 minus 3 by 4 z minus 1. And this is supposed to be minus 3 by 4 since it's a plus. It's supposed to be plus over here, my bad. It's supposed to be plus over here. So it's 1 minus minus 3 over 4 z minus 1. So when we look at this, we can see that it is of this form now, where a is equal to minus 3 over 4. So we can simply write h of n is equal to a power of n. So a is minus 3 over 4 power of n times u of n. And then of course we have the 3 outside here. So we're just going to put the 3 over here. So this is our h of n for case 1, which is done. So for case 2, we can write it in the same form, which is h of z is equal to 3 divided 1 divided by 1 minus 3 over 4 z minus 1. Alright, so we can use this formula because it's of this form now, where a is still minus 3 over 4, right? So we can write it, h of n is equal to 3 is outside, so we write 3 first. Then we have a minus at the beginning, so just put the minus here. There's a minus 3 over 4 inside here to the power of n. And then we have the unity function n minus 1. That's as simple as that. So we've got the h of n for both cases, for both regions of convergences. So this is for case 1 and this is for case 2. So let's go to a different example. The example over here is h of z is equal to 1 plus z minus 1 plus z minus 3. So in this we can see that the region of convergence obviously is for z is equal to greater than 0. Because if you plug in 0 into this function goes to infinity. So we can rewrite this function as z power of 0 plus z power of minus 1 plus z power of minus 3, since 1 is equal to z power of 0. So we're going to be using this property, which is property number 4 from the Z-transform table, which is delta, which is the impulse response, n minus m can be transformed to z power minus m in the z domain. So when we look at this, it's a summation of three of these. So this is delta n minus the power over there 0 plus delta n minus the power over there 1 plus delta n minus the power over there 3. So this will equal to delta of n plus the delta of n minus 1 plus the delta of n minus 3. So this is the inverse Z transform for this function. That's all from me. Thank you.
Good evening everyone. Today I'm going to teach about the partial fraction expansion. So for the general equation for hz, the equation is like this. The summation of m k equal to 0 b k z negative k divided by summation of n k equal to 0 a subscript k z to the power negative k. So I'm going to teach about for n, the denominator is bigger than m, and for another case, m is bigger than n. So for n bigger than m, for the hz, the equation is summation of m k equal to 0 b subscript k z negative to the power negative k over summation of n k equal to 0 a subscript k z to the power negative k. So the final equation is like this. For ak equals to 1 minus dkz to the power of 1 hz, where z equals to dk. We're going to show the example. So find the hn of hz 1 minus 2z negative 1 over 1 minus 5 over 6z minus 1 plus 1 over 6z minus 2. For z, modulus of z bigger than 1 over 2. So first of all, we re-expand this part. Firstly, we multiply with 6 and then times with z to the power of 2, then insert in calculator, so we find the poles. So this is the equation. Hence, we separated it like this. a1 over 1 minus 1 half z negative 1 plus a2 1 minus 1 over 3 z minus 1. So after this, we are going to proceed like this. a1 is equals to 1 minus 1 over 2 z power negative 1 hz, whereas the z is half. So this is following this formula. So after this, we insert to the main equation, we get 1 minus 2z power negative 1 over with 1 minus 1 over 3 z negative 1 z half. So after this is because the 1 over 2 here is cancelled out by this, so the denominator is this thing. And after that, we solve, we get 1 minus 2 by 2 over 1 minus 1 over 3 in bracket 2. So the final answer is negative 9. So for a1, we get negative 9. So next, we're going to proceed with a2. So for a2, we have 1 minus 1 over 3 z negative 1 hz divided z is equals to 1 over 3. So we insert in the main equation z, substitute z, we get 1 minus 2 z negative 1 over with 1 minus 1 over 2 z negative 1 where z is equals to 1 over 3. After we substitute the value of z, we get the answer is equals to 10. So after all of this, we will get the answer of hz is equals to negative 9 over 1 minus 1 over 2 z negative 1 plus with 10 1 minus 1 over 3 z negative 1. So if we follow the table number 5, pair number 5, we got the hn is equals to negative 9 1 over 2 to the power of n un plus with 10 1 over 3 n un. So this is the case for which n is larger than n. So we are going to proceed with the case where m is larger than n. So I have one question over here. So find the hn of hz is equals to 1 plus 2z to the power of negative 1 minus 5z to the power of negative 2 plus 6z to the power of negative 3 over 1 minus 3z to the power of negative 1 plus 2z to the power of negative 2, provided the z value modulus is more than 2. So first of all, we are going, as we can see, the m is greater than the n, so we need to long division 1 minus 3z negative 1 plus 2z negative 2 divided by 1 plus 2z negative 1 minus 5z negative 2 plus 6z negative 3. So we are going to start from the n, multiply with 3z negative 1, 3z negative 1. So we got, the answer is 3z negative 1 minus 9z negative 2 plus 6z negative 3. So after we calculate, we get the answer 1 minus z negative 1 minus 4z negative 2 and 0. Then we multiply with 2, we get 2 minus 6z negative 1 plus 4z negative 2. So the final answer is negative 1 plus 5z negative 1. So right here we got the equation like this. This is the division, this is the remainder. So what's next is we take the, put the hz here, 2 plus 3z negative 1, and we take the remainder as the denominator of the equation, negative 1 plus 5z negative 1 over, this is plus 1 minus 3z minus 1 plus 2z negative 2. So this thing will remain, and for this particular part we are going exactly the same as we did for n larger than m. So that is for partial fraction expansion for case n is larger than m and m is larger and equal, m is larger than equal to n. Thank you.
Hi, Labib here. So I'll show you how to do inverse Z-transform when you have more than one poles which are similar. So this from M5 and this example 6. So you have this function hz, as you can see here, and we have to use inverse Z-transform to convert it to hn. Alright, so let's begin. So you have three poles here, as you can see from here. So the poles are z equal to 1 and okay, z1 equal to 1, z2 equal to 1 over 2, and z3 is squared here, right? So z3 is also equal to 1 over 2. Alright, now you have m and n when it comes to these type of questions. So m is the order of your order of numerators, n is your order of denominators. So if you, when you look at this question, you can obviously see that n is greater than m. So the denominator has higher order than your numerator. So it's n greater than m. So if this is the case, you don't even have to think about long division. Alright, so first of all, before we do anything, we must use partial fraction. So partial fraction, let's do this. Okay, so these are function, and in partial fraction form it will be a1 over 1 minus z to the power of minus 1 plus c1 over 1 minus 1 over 2 Z minus 1 plus C2 over 1 minus 1 over 2 Z minus 1 square. Okay, so I want to represent this function in terms of partial fraction, like this. Alright? So now we have to find the numerators, A1, C1, and C2. So how do we normally find them? Okay, so this is how we usually do in class. So let's say you want to find A1. So we must multiply the numerator of A1, 1 minus Z minus 1, with the overall denominator. Sorry, not the overall denominator, with HZ. So, okay, this is what you get. And then you must substitute the poles for A1. So the poles is Z equal to 1. In this case only. In this case. So, okay, so after you multiply HZ with this, you only have Z to the power of minus 1. This is cancelled out. So 1 minus 1 over 2 Z minus 1 square. And then Z equal to 1. Okay, so A1, now you just substitute 1 into Z. Okay, so substitute 1 to the numerator. We have 1. Then 1 minus 1 over 2. You have 1 also, so just 1 over 2 square. So what is the result for this? The result for this, you will get 4. Okay, so this is your A1. You already found your A1. Now, you need to find C1 and C2. First of all, I'll show you how to find C2. And C1, I'll tell you slightly a bit later. Okay, so you have C2. Okay, so just same like A1 over here. You have the denominator 1 minus 1 over 2 Z minus 1 square. You multiply with HZ. And what are the poles here? The poles here are 1 over 2. Z equal to 1 over 2. So you must substitute Z equal to 1 over 2. Alright. So after you multiply HZ, this part is cancelled out. So you have Z minus 1, 1 minus Z. Sorry, it's not clear. 1 minus Z minus 1. Okay, so we now all we need to do is substitute Z equal to 1 over 2. Substitute 1 over 2 into this equation. So after we do that, we get 2, 1 minus 2. You can substitute into this and find this actually. So after this, our answer is minus 2. So this is our C2. We have A1 and C2. Now, okay, to find C1, we cannot use this method because you see, for C1, if we multiply the 1 minus 1 over 2, so 1 over 2 Z minus 1 with the HZ, what do we get? We get Z minus 1, 1 minus Z minus 1, and then we have 1 get 1 minus 1 over 2 Z minus 1. So you cannot use this function because you have two poles. So you cannot solve it like that. That is why what we'll do is we'll combine this whole function together with what we have. So let's erase this. And we'll combine this function. So a1 1 minus 1 over 2 z minus 1 square plus c1 1 minus z minus 1 1 minus 1 over 2 z minus 1. And for C plus C2, we have 1 minus Z minus 1. And this will be, your denominator will be the same as AZ, Z minus 1, 1 minus 1 over 2, Z minus 1 squared. Okay, so this is your function. And now what we have to do is compare this one with this one. So we have to expand the numerator. So expanding the numerator, we get this 1 minus z minus 1 plus z minus 2. Okay, so this is the numerator, a z minus 1 plus z minus 2 over 4. Okay, so I'm just combining the numerator here. So C1, and when you expand this thing, you have 1 minus 3 over 2 z minus 1 plus 1 over 2 z minus 2. Okay, plus, sorry, I don't have enough space. C2, 1 minus z minus 1. Okay, so this is our whole numerator. So we have to find C1 by comparing this whole thing with z minus 1. So just expand this part. We don't need to like expand the whole thing because the 1 and z minus 2, we don't have z minus 2 here, so they will become 0 anyway. So all you have is a1 minus 1 plus c1 minus 3 over 2 z minus 1 and plus c2 minus z minus 1. Overall, in the end, these are your, this will be your numerator, and you have to compare it with your with your numerator at HZ. So just put in the values of A1 and C2, and we can get minus 4 Z minus 1 plus 3 over 2 Z minus 1 C1. C2 is minus 2, so plus 2 Z minus 1. Okay, so Z minus 1, you can cancel Z minus 1 on both sides, and then you take the 2 and 4 to the other side, and okay, let's move to this side. So okay, so okay, Z minus 1 is cancellability, so minus 3 over 2 C1. After you take the minus 4 and minus 2 to this side, we get 3. So C1, you can take this whole fraction this side, and we'll have the 2 cancel out, and you'll have -2. So it's the same as C2. So you have 4, -2, and -2, and your equation will be, overall your equation is 1 minus Z minus 1, sorry, AZ, we are representing as this. So 1 minus half Z minus 1 minus 2, 1 minus half Z minus 1 squared. Okay, that's it. And now all you have to do is use the Z-transform table, inverse Z-transform table, to convert this to Hn. So for this, we can just use the rule 5. So for rule 5, stop here. Okay, so we have this function here, and now we just use the Z-transform table. In this case, we just need to use the second rule, fifth rule, and seventh rule. So for this one, we get is sufficient if we just use the second rule. So 1 minus 1 minus Z minus 1. So you take out the numerator, so 4, and then you can just place this one. Because when you take out 4, you have 1 here, so it will be like this one. And then you can just place this function. And then for this one, we need to use the fifth rule. So we take out the 2, and then you have 1 here. Then we can use this function. In this case, the a is 1 over 2. All right. So therefore, our inverse is for this one, and for this, we use the 7 function. We use number 7, and then all we need to do is, so we get, if you do the calculation, you'll get 4n plus 1 half n plus 1 u n plus 1. You just need to make some adjustments for this, and then you'll get this. So that's it. This here is your Hn. And that's all for example 6. Thank you.
Hi there, I am Azwad a third year Mechatronics Engineering student from UTM. Today we are going to study about Z-transformation, a very important topic in the field of digital signal processing. Let's go!
When we talk about Z-transformation, we have to remember the Z-transform properties. So let's go, let's dive in and find the answers. First of all, we have linearity. When we talk about linearity, for example, you have an equation like this. So what you do is, when you have a two separate h of n, you do Z transformation separately for each h of n. That's simple. Regarding time shifting properties, we see that if you have a delay in your discrete time function, you just put that delay in the front with the z. You just put z to the power minus nd, where nd explains the delay of the system. Regarding scaling in the z domain, we can see when you have an hn, where an represents your scaling, all you have to do is put z over a on the final answer of h of omega. You have a of n on the front, so you just take the a, put it below on your z transformation and put it just below z, and you're done. It's as simple as that. No need to worry about it. Regarding time reversal, so if you reverse the time the other way, which is h inside h negative n, when you have h negative n, you basically just write like this: hz to the power minus 1. That's it. As simple as that. You're done. So I'll be covering this linearity, time shifting, scaling in the z domain, and time reversal for my video. Let's see some examples. Alright, so let's start with the examples. First of all, if we look at example 7, the question asks us that hn equals to minus 1 over 2. We have this function basically. So on this function you can see that there are two functions. This one, this one. So they're separate. And that's where we can use our linear transform properties. So we just do Z transformation separately for this one, and we do Z transformation separately for this one. So if we go back to our table, then from the table we can see this will give us hz equals to 1 over this and plus 2 divided by 1 minus 1 over 3 z to the power minus 1. It's just basically take from the table and you're done. There's nothing to be worried about for this kind of questions. Now if we move to the issue regarding what it will be the ROC of the event, we can see that according to our transformation properties, ROC is ROC1 intersecting with ROC2. So from here we see that ROC1 was z greater than half and ROC2 was z greater than 1 over 3. So here's the diagram. We can see from the diagram we can see 1 over 3 greater than 1 over 2 greater than. So our intersect for both of these will be z greater than 1 over 2, basically the outside region. So that's why we have z is greater than 1 over 2. So that's done with the first example of linear properties. Let's go to the second example of linear properties, which is example 8. On example 8, we can see that it's the same. We have two different functions separated by a plus. So basically you just do Z transform for each of them separately. From the table we can see that the first one will give us 3 z to the power minus 1. It's the equation number 4 from Z transform pair table. And for the second part we will have 2, which is a constant, over 1 minus half z minus 1, which is equation pair table equation number 5. And for the ROC it's the same as before. We can see that for the first one our ROC is z greater than 0. It can be any number basically. On the other hand, for the ROC2 we see z is greater than half, z is less than half, and that's why from here if we do the intersection z greater than 0 and z less than half, you will see we find z is in between 0 and half. Now let's move towards example number 9, which considers the other properties. Alright, now regarding the second properties of our question, which was referring to the time shifting, we can see that in our question we have del n minus 3. Now this minus 3 represents a delay of 3, and here we have n minus 2, which represents a delay of minus 2. So let's just do the normal way. This is also linear properties because they're separated by a plus, so you do them separately. For the first one you use pair table number 4, pair table from pair table use equation number 4, so it will basically give you z to the power minus 3. This minus 3 is for the delay, and same with this one. This one is equation number 5 from the pair table. You will get this one. And regarding z, we know that z will be greater than 2, because we all know that z. Yeah, it's pretty clear from here. You can see that for the function to work, it's only when z is greater than 2 and that the function, the modulus of z greater than 2, that you'll find a reasonable function. Now moving to the next question, which is example number 10. Which is also from the time shifting. Now in example number 10, we also see there is a time shift, there is n minus 3 and there is n minus 2. Now in this question, we have to remember, if you look closely, you will see that there is no plus in between. The whole thing is one function. And if it's one single function, then the value of n has to be same. Otherwise, there is no transformation, there is no equation from the pair table that you can use. So what we can do is, for this question, we saw that there's n minus 2 here. There's nothing to change right here. But what we can change is this n minus 3 from here. So we write it like this. N minus 3 can be written as n minus 2 minus 1. Now this minus 1 can be taken separately. Rather than taking common, we take it separately. So we have half to the power minus 1 times half to the power n minus 2. And this one stays the same. And so we know half inverse will give us 2. This one stays the same, this one stays the same. But now this one can be found from the pair table. So if we look at the pair table, we will see that this one resembles the same as equation number 5. So 2 stays the same. Oh, wait 1 second. This is not equation 5. My bad. Just a second. All right. So on this equation, what happened is, we have, this is our a to the power n, you have un, and there's a constant. So it is equation number an un, yeah, it's equation number 5. But it uses equation number 5 to find the basics, but we also have to remember that there is n minus 2. So we also have to consider the delay. So when we consider the delay, that's where the minus 2 comes in. So if you do the function, 2 will stay as it is, and using the pair table, you will find that we have a function like this, where this represents the a in the function, and we have z minus 2. This minus 2 is because of the delay. So we're done with example number 10. Let's move to example number 11. Now, example number 11 is considering z-domain, scaling in z-domain. So let's see what we can do with scaling. For the first question, it's very simple. In example 11, if hn equals to un, then what will be h to z, where h to n equals to 2 to the power n hn. So it's basically the same function, but this time we have a scaling factor in the front. So what we can do is, as we have seen from our linear transform properties beforehand, we can see that all that it does is basically, there's a minus 1 at the it basically does z over a all the time. Let me explain. So on this equation, on the normal one, if we consider, we will see that if hn equals to un, we can find from the pair table that the answer is hz equals to 1 over 1 minus z to the power minus 1. So that's the answer for the initial part. But we have a scaling of 2 to the power n from the pair table, from the properties table, if you remember correctly, which clearly mentions that if there is a to the power n, we basically do a z over a. So basically just do the same here. There was a to the power n, which is 2 to the power n, So we do z over a. So before z was this, now we write z over a, where a is 2, so z over 2. Now if you simplify it, you will find 1 over 1 minus 2z to the power minus 1. Now this was a clear-cut example, but consider example number 12. In this one, we have, it's still simple, but they have used some other factors as well. In example number 12, you will see that the question has a function, has the linearity properties inside, but the multiplication of the scaling is outside. So the scaling happens for all. So we can use two different methods for it. One, we do time shifting, then do linear properties, or we just scale the whole thing in the z domain. So let's consider method number 1. In method number 1, we have to do time shift, then we have to do linear properties. So for the time shift, just multiply everything with 2 to the power n, you'll find this. Now for every single point, because this one, del n represents n at 0, so 2 to the power 0 gives us 1, that n minus 1, so n at 1, delay of 1, so we have 2 to the power 1, which gives us 2, and 2 to the power, as this is n minus 2, you have 2 to the power 2, which gives us 4. So this is our function. We have done the time shifting. Then we have three separate functions, so you just do Z-transform separately, which will give you an answer of 1 plus 2z to the power minus 1 plus 4z to the power minus 2. But using method 2, we just consider the inside first. Forget about the 2 to the power n scale factor in the front. So if you just consider the inside, we will see that in linear properties, Z transform will give us 1 plus, will give us this, basically. Then we consider the scaling factor. We know that initially it was hz, but when we have a scaling factor of 2, we divide z by 2. So we have h1 z by 2. So the same function, but the z is substituted by z over 2, which will give us this. And if we simplify the function, we will find the same result as before. Now the last question we have is regarding the time reversal, which is example number 15. The time reversal basically considers that you just rotate the time the other way. It's simple as that. So if you have a minus n, which basically represents a rotation of the time domain, of the time scale, discrete time scale, you just basically write z to the power minus 1. That's it. So you have a initial function. So if you have a function like, for this example, x n equals to this, y n. So if they're asking for yz, if y n equals to x minus n, there's a minus there. So it's the same. Initially consider the x. You'll find that xz will give us 1 minus this from the pair table. And for the yz, all you have to do is rotate the z, or z to the power minus 1. Now we already have a z to the power minus 1. If you rotate the z, which will give us 1 over z to the power minus 1, basically they will cut out. Z to the power minus 1 times z will give you, just rotate the z, you'll give it 1 over z, you still have minus 1, and if you inverse 1 over z, you will get z. So you get an answer yz equals to 1 minus 1 minus 1 over 1 minus az, and that will be it. Thank you very much.
Hello there. Thanks for my member in explaining for the first 4 the property of the Z-transform properties. And I here will continue the 3 more of the Z-transform property, with which is the derivative, conjugation, and convolution. So let me give a brief, a small brief of these 3 properties. The derivative is an instantaneous rate of change of a function with respect of its variable. Conjugation is a process of complex number which the imaginary number changes its signs. And lastly is a conjugation. It's a mathematical operation on the on two function to produce a third function. For more understanding, let's continue by doing some exercise. So, firstly we will talk about the differentiation. So, from an example, from the Z-transform table, we know that un is equal to Z function. So, we transform into Z function, which un is equal to then we continue for differentiation, which hz is equal to so by using the quotient rule, which differentiate uv is equal to u prime v minus u v prime over v square but before that we will simplify the formula for easier to differentiate by multiply the equation with z. So from the differentiation and the quotient rule, we will get next, we will simplify the equation. And we will get after that we will divide times by z, 1 over z, and lastly we will get z minus 1, 1 minus z minus 2 square. So this is a solution for differentiation. So we will go to the next question. For the second part is conjugation. So if it's given as Hn is equal to exponent Jn un, from the Z-transform table, we will get Hz is equal to 1 over 1 minus exponent J Z negative 1. So if it's given H1n is equal to conjugate of Hn equals star, thus H1 Z is equal to H star Z star n 1 over 1 minus exponent negative J Z negative 1. So we can see the difference is positive and negative, which changing the polarity. So for the last part is convolution. If it's given as x1n, the function of x1n and x2n, conversion of yn is equal to x1n convolution to x2n, and we will find yz. So we will know that x1n is equal to which transform into z, x1 z equal to 1 plus z negative 1, and for x2 similar to x1, and we will transform x2 into Z-tranform, and we will get so yz is equal to x1 z x2 z, which follow the table of convolution, which we will get that's for the solution of convolution.